Okay, here we are with Proofs 3 lecture. You'll notice that this is very similar to what we've seen before with Proofs 2 and Proofs 1. There's now a new thing to do. So notice here in part A, if you decide that the proposition is true and the proof is correct, then you need to state, or then you need to circle, which of the three different types of proof that we've studied, direct, contrapositive, or contradiction, was used in the proof. All right, so with this example, this proposition is true and the proof is correct. Okay, so this is going to be an example of how to, once you've decided that the proposition is true and that the proof is correct, then you get to, this will be an example of how to figure out if it's direct, contrapositive, or contradiction. All right, first let me read through the proof and just talk about that. Okay, so the proof is saying that no matter which integers x, y you pick, if it's true that x is greater than or equal to 2, then x does not divide y, or x does not divide y plus 1. So the thing to notice here is that these symbols here, these are does not divide. Not divides, but does not divide. All right, so we assume that x is greater than or equal to 2. Nothing different there. That's assuming that, right, this is P, this is Q. It's an if-then, so we have P implies Q. So we assume P. And then notice what we assume here. We assume, see, Q is an OR. So let's see. Now we suppose this, and notice that the knots, the knot does not divide for each of these has been taken away. So Q is x does not divide y, or x does not divide y plus 1. So let's see, let me give myself some room here. Not Q is going to be the negation of x does not divide y, or x does not divide y plus 1. Using De Morgan's law, that tells you that x divides y and x divides y plus 1. So what I'm saying here is that here we assume P and here we assume not Q. So we assume P and not Q. So because we assume P and not Q, and you know that the proof is correct because I told you it was, then we can see that this is in fact a proof by contradiction, right? Because a proof by contradiction, in a proof by contradiction, you assume P and not Q and derive a contradiction. Now, of course, you would have to go through and see if the work in this proof is correct before you knew all the other stuff in the proof is correct. That the assumptions are stated, that we use correct rules of logic, everything follows from the next, everything follows from the line that came before. So let me just explain the proof here. All right, we assume P and not Q. All right, that's what I already said. Okay, so now if x divides y, that means that xn equals y, where n is an integer. And if x divides y plus 1, that means that xm equals y plus 1, where m is an integer. All right, and I chose this proof because you've been studying a lot of proofs, and it's time to show you that proofs can be rather creative. And here's a nice little creative trick for this proof. So the proof writer, what they do is they multiply so when I wrote this proof, this is what I first came up with, was this here. And then I thought, oh, okay, I could backtrack and make it look like this. And then when I wrote the proof, it looked the way it does now. Now, I actually didn't come up with this proof on my own. I found this from another professor's stuff online, and I read it, and I liked it. And I thought it was a good proof, but I changed some things. I thought that made it a little easier. Okay, but in any case, now when I say easier, don't take that the wrong way. Don't mean that it's easy. It just means that maybe I cleaned up the logic a little bit. Okay, so just try and follow along and see x times m minus n, right, is the x. So if you distribute here, right, you get xm minus xn. And then we know that xm is y plus 1, so that's xm there, and then minus xn. And so that becomes 1. And so because now, really important thing to notice here, right, is that we declared our variables here. We defined what n and m were. N and m are integers. So because they're integers, that means that m minus n has to be an integer. So that tells us that we've satisfied the definition of divides. And so then we know that x divides 1. Now think about this. Divides only works with integers. So the only integer that could divide 1 is 1 or negative 1. So if x divides 1, that means that x is equal to 1 or negative 1. And in either case, 1 is less than 2, and negative 1 is also less than 2. And that's our contradiction. Right, so we assume P and not Q, and then we derive a contradiction. All the work in here getting to our contradiction is true mathematical work. So the thing that must be wrong, if this is all true mathematical work in here, is this must be wrong. So if that's wrong, it must be that not Q is wrong. If not Q is wrong, that means that Q must be right. right? Because if we know that not Q is false, it must be that Q is true. This is because all mathematical statements are true or false. Okay, so x is equal to 1, and so our contradiction is that x is less than 2, but we assume that x is greater than or equal to 2, right? So this is a contradiction. This is a statement that can never be true, right? So think about this, right? If so we have P is x is greater than or equal to 2. But we also have this right here. This is not P. X is less than 2. And so what we've shown is that if not Q is true, then what do we get down to? Oops. We get down to, we find our way to P and not P. And that's a contradiction. P and not P can never be true. If P is true, then not P is false. True and false is false. If P is false, then not true, then not false is true. False and true is false. This will always be false. And so we have P and not P. So it must be that our assumption, not Q, is false. Therefore, Q must be true.